Thanks. So this is my first experience of giving a seminar on Zoom, so we'll see how it goes. It's quite different, I think, from actually seeing people face to face. So some of you will probably know I did retire from the same MP group at UCL last October. I think that was quite good timing, so I've missed all the hassle of online teaching and whatever. But I am still involved in some research projects, which keeps me interested, which is good. And one of these is actually a big program grant that's led by Leeds University, which is a joint modeling and theory and experimental project. So my involvement in this is looking at all aspects of crystallization, and I'm particularly involved in the additive directed crystallization, which means that using impurities and additives to actually control crystallization. So there's a few of us at UCL involved in this: Ian Ford and Robert Darkins and the student Alex Broad. However, I'm not going to talk about that today. Hopefully you'll hear about that at some later date. I'm going to talk about my other interest today, which is basically modeling radiation effects in solids. I've had this long-term aim that I'd like to develop and apply methods for accurate and large-scale modeling of the structural evolution of materials following radiation that excites electrons. So originally was concerned about radiation damage for nuclear materials, but more recently it's become clear that this is actually relevant to nanotechnology in terms of nanostructured materials or even phase change materials for memory devices. And the types of radiation that excite these electrons are very high energy, ion radiation and laser radiation. So broadly, radiation has two effects when it impacts a solid. It can either interact with the atoms or it can excite the electrons, or of course it can do both simultaneously. In terms of interacting with the atoms, classical MD in the form of cascade simulations have actually been very successful in modeling this type of radiation damage from several decades. However, in terms of exciting electrons, this is more challenging. Clearly, the quantum effects are very important, but this has been modeled by experimentalists again for several decades by using the two-temperature model. And this effectively means that if you excite the electrons, you can have two different temperatures for the atoms and the electrons, and these couple via electron-boson coupling. So this two-temperature model basically takes these two temperatures and evolves them in space and time in a coupled way, and they're coupled through the electron-boson coupling. However, one major limitation of this type of modeling is that all you get out of the model is temperatures, and you don't get any atomistic detail. So you can't actually see what happens to your structure over time or what the residual damage is at the end. But another way that the electronic excitations can couple to the atoms is through the modified interatomic interactions. If you excite the electrons, you clearly change the interaction between the atoms. And this isn't really taken into account by the two-temperature model. It can be, some of the effects can be modeled by ab initio electrodynamics. However, clearly the length and the time scales are very limited with this approach. So in order to overcome some of the limitations of the two-temperature model, we work with two-temperature electrodynamics, which effectively just couples the two-temperature model with classical electrodynamics. So here we have the laser pointer. Here we have the two diffusion equations for the electrons and the lattice, and they're coupled with this electron-photon coupling points. So we can basically evolve this in time. So the idea of the two-temperature electrodynamics is that we replace this lattice thermal diffusion equation with molecular dynamics. And this is a schematic of how we actually do it. So in the middle, we have our atomistic simulation with our atoms that we evolve with molecular dynamics. And then superimposed with this is a grid of voxels, in which of these voxels you get a particular electronic temperature defined in each of these cells. So we solve the thermal diffusion equation with a finite difference technique, and then energy is exchanged with these little separate voxels with the electrons, between the electrons and the lattice, and it's exchanged by this Langevin type thermostat. So effectively what we're doing here is we're thermostating the lattice for the electrodynamic cell with a Langevin thermostat. And the temperature of the Langevin thermostat is the local electronic temperature. So that, is in a nutshell, is basically the two-temperature electrodynamics model that we use to include electronic effects in these radiation damage simulations. So initially, as I said, we wanted to look at some radiation effects, where they were basically including these electronic effects in our cascade simulations. And this is a picture, I think, of probably of the paper from a collaboration with Martin Duffy and people Costia from Queen Mary. And what you get of this is basically point defects and clusters of defects. However, we realized that it could be used for other types of simulations, other types of radiation effects, and one is swift heavy ions. Swift heavy ions actually deposit a lot of energy into the electrons along their path. So you can actually model these by depositing energy along a linear path in our simulation cell, and then evolving this energy will actually couple to the atoms, and you can evolve the simulation of that. So we've done these type of simulations in both metals and in silicon. And metals, you see something quite, in both cases, you get these very elongated regions of damage. But in metals, you see something quite interesting, and then that you actually get dislocation loops followed along a path of the initial ion track, which has actually been seen many years ago in experiments. However, my focus today is on lasers. So in lasers, you clearly will deposit the energy directly into the electrons. So we can model the effect of actually laser radiation of thin metal films. This is a project that we did in collaboration with Alex Luger and an experimental collaborator from Osaka University, Professor Tanimura. So what he was doing, he was actually firing these very intense, very fast, as in femtosecond lasers onto thin metal, single crystal gold films, very thin, so either 10 nanometers or 35 nanometers. And then what he did, he would measure the diffraction pattern and see how it changed over time. And this is basically investigating the melting or the phase change of these metal films in response to this laser radiation. And you can see some of the results here. So basically, for relatively low fluences, the diffraction, one particular diffraction peak will decay, but after 30 picoseconds, it hasn't decayed to zero. So that is really indicating that you haven't got complete melting of your film. But if you increase the fluence, you get melting within about 20 picoseconds, as you see here, and increase the fluence even more, you get faster melting, as you'd expect. So this basically was showing them how fast you could melt your films with a laser. So when we saw this, we realized that actually both the time and the length scales were very relevant to what we could actually do in terms of our modeling. So we could model exactly the same thing, and we knew all the parameters in our two-temperature model for these. We can either calculate them with DFT, or they were known from experiment. So we could actually calculate exactly the same things that we're measuring. So for the lowest fluence, these are our results. These are two different diffraction peaks, 200 and 220. The dots are showing the experiments, and the solid lines are showing our modeling results. So basically what happens to the diffraction peaks over time in response to when the laser hits the film. And you can see that the agreement was remarkably good, especially since we've none of these are fit to the no-free parameters. So because we actually fit the experiment, we can now say not only do we know how fast this melts, but we can see this in atomistic detail. And this is the top one's a picture of basically the order parameters over time. So if it starts melting at the surface, which is what the red one shows, and the melt front moves through the solid, and even at 0.15 nanoseconds. It hasn't actually totally melted, but some crystalline material left. So we get all sort of atomistic detail, the density, the temperature, everything from our simulations. So we're arguing that this was actually, but first of all, it showed that the two temperature model worked very well for this particular system. And now we say that because we can say exactly what happens from the atomistic point of view. Same thing happened if we increase the fluence a bit. You get slightly different types of melting. Here again, we've got the solid lines. We're agreeing these are three different diffraction peaks. The solid lines agree very well with the experimental points, which were the dots. And again, we can see what's actually happening in great atomistic detail. And here we get something called homogeneous melting, where the melt front doesn't necessarily move from the surface through the center, but you get pockets of melting being nucleated throughout the thickness of the film. So we can see the transition between homogeneous melting and heterogeneous melting. So then the next step was to do the higher fluence. And here it was quite disappointing because our results are the dotted lines here, and the experiments were clearly the dashed line experiments are the dots. And initially the agreement wasn't good. So what was the difference between this experiment or this model and the other ones, which agreed very well? So the only thing to really think of is that there's such a high fluence that we're affecting the interaction between the atoms. Before we were just using the ground state potentials for gold, but if we actually expect the interaction between the atoms, then perhaps we should model these. And people had actually developed some what they called electronic temperature dependent interatomic potentials for gold. And we tried those, we modified them a bit to correspond more to our system. And by doing that, we could actually reproduce the melting or the disorder induced by the laser at these very high fluences. And this is a picture, but these are now thicker films because the very thin films would actually disintegrate completely. But this is a picture of atomistic scale, what happened if we included these, what we would call excited state potentials. So what we have here is what the norm thermal forces due to the change of the interatomic potentials would actually accelerate in melting and make it happen much faster. But then how are we going to know when we should actually modify the interactions between the atom because we've excited the electrons? So for this, we turn to finite temperature density functional theory calculations. And one thing did was actually, these calculations were done by Evelyn Girey and Alex's group. One thing was actually to look at what happened to the cell parameter. How did the cell expanded if you increase the electronic temperature, no, not the lattice temperature, but the electronic temperature. So running these high temperature density functional theory calculations for different electronic temperatures, you can see that the lattice parameter is flat for quite a long time. But once you start getting to electronic temperatures of about 10,000 Kelvin, it actually increases quite rapidly. So you might guess from this that the effects on the interatomic interactions might kick in round about 10,000 Kelvin. Another thing you can look at is actually the phonon dispersion curves. Do that at ground temperature, at room temperature, we see there's a red curve here. If you do it at excited state temperature, in which case it's actually 15,000 Kelvin for the electronic temperature, you can see that the phonons are softened across the board. So this seems to suggest that somewhere between 10,000 and 20,000 Kelvin, we should modify our interatomic potentials if we want to do these types of simulations. So we then moved on to tungsten. Clearly tungsten is a very important metal. It's used in lots of extreme conditions, especially things like fusion reactors. So first of all decided to look at the phonon dispersion for tungsten, and this came up with a bit of a surprise. So the black line here is the ground state, the 300 Kelvin dispersion curve, which it agrees very well with the experiment. But the red lines are the same thing done at 20,000 Kelvin. You can see here the reduced imaginary frequencies, which is signaling that we must have some sort of lattice instability. So being a metal, what would the lattice instability be? So you might expect, so BCC is the ground state structure. Possibly it changes to FCC at high electronic temperatures. So we're looking at the free energy as a function. So we can do a continuous transformation between FCC and BCC, or in this case, BCC to FCC, along the Bain path. So basically by stretching or contracting along the Z direction and doing the opposite along the X and Y directions, we continuously transform, in this case, FCC into BCC. So you can calculate the free energy along this path, both for the ground state, or both for the 300 Kelvin case and the 20,000 Kelvin case. The 300 Kelvin, as you can see, as you'd expect, BCC has got the lowest free energy. But at 20,000 Kelvin, actually, the FCC has got a lower free energy. And there's no barrier between this. So you can actually, if you excite it up to 20,000, you could transform to FCC lattice without any barrier. So this is suggesting something really interesting is happening to tungsten if you excite the electrons. So investigating this even further with ab initio MD, in this case CP2K, and these calculations were helped with these with Matt Watkins, again from Alex's group, who's an expert in this code. So basically what we did start off with an electronic temperature throughout the simulation of 20,000 Kelvin, but start off with the BCC lattice and just run the simulation. You can see that in a very short time, so less than a picosecond, our BCC lattice expands in one direction, contracts in the two perpendicular directions, and turns out into an FCC configuration. Here, the green atoms are showing an FCC configuration, and the red atoms are showing HCP. So effectively, what here we've got all FCC with a stacking fault, which shows up as HCP in the simulations. So the high temperature, finite temperature DFT calculations actually reproduce this transformation BCC to FCC in tungsten. But of course, we're limited in the size of the simulations we can do with ab initio MD. What we really want to do is large scale simulations. So you want to do these simulations with a classical interatomic potential. But how we can do this, and thinking about it for some time, was actually having an electronic temperature dependent interatomic potential. So as you change the electronic temperature, i.e. you excite the electrons, then you change the interatomic potential. So by doing some very, very basic fitting to some of the properties, the free energy versus lattice parameter, we can actually develop a set of electronic temperature dependent interatomic potentials for tungsten. The red one here is the ground state when we start at. I think it's a basic modified Finnis-Sinclair potential. And then if we increase the electronic temperature, we get a full set of potentials that change gradually. And you can see that both the depth of the well decreases as you increase the electronic temperature, and also it moves out, the position of the minimum moves out. So effectively what you're having here is two effects. One is that the lattice parameter will expand when you increase the electronic temperature, and the melting temperature will decrease. That's a feature of both these. So we now have a complete set of electronic temperature dependence for potentials for tungsten. So we can test this by actually comparing it with the ab initio MD calculation. They're doing exactly the same thing, basically. Very small simulation cell, think 1,000 atoms, and run the simulation by starting with the electronic temperature dependent potential for that particular electronic temperature, i.e. 20,000 Kelvin, and just let the simulation run and see what happens. So it starts at BCC and it actually transforms into FCC in a similar time scale in the ab initio MD. So this seemed to be quite convincing that our potentials were at least capturing the main effect of these particular change of the interatomic potentials with the electronic excitations. What you see here, we don't actually get the stacking fault in this case, but this is not necessarily a feature. The other point to put out that these potentials were never fit to FCC. They were only fit to the change of the free energy with the BCC and never to the FCC. So actually it came as a little bit of a surprise that actually this worked in terms of capturing the transition. So then we're in a good position to actually do our large-scale molecular dynamics with excited electrons. But we tried this with those a big outstanding issue, and that was energy conservation. They didn't conserve energy, and actually it isn't very surprising, because if you run a typical two-temperature model two-temperature MD simulation here for the lattice temperature and the electronic temperature changes continuously throughout the simulation. So that means you're actually moving between these potential energy surfaces continually throughout the simulation. So this energy has to come from somewhere or go to somewhere in the simulation, and that wasn't being captured by our model. So to solve this one, we actually had a collaboration with Leo Ma at Cullen, because when he was presenting this work, he suggested we go back to the original derivation of the two-temperature model, or the two-temperature MD, and then see what happens. So if you're at actually a Hamiltonian of the sum of the kinetic energy, potential energy, and then electronic temperature term, and now we realize that our potential energy is now also related to the electronic temperature, and derive the equations. So instead of just having where the heat capacity comes in our electronic thermal diffusion equations, if we change this heat capacity not only to regard the electronic energy, but also a potential energy term, this actually solved the problem. And now we can conserve energy. So we have our two-temperature MD, which actually gives us an evolution of the electronic temperature. We can change our interatomic potentials depending locally on what this electronic temperature is, and we can run the simulations. But something I would like to point out is that we have to be very careful here, because if this condition down here holds, then our electronic heat capacity is less than zero, and that really isn't very good news. It's unphysical, but also the simulations blow up spectacularly when this condition is actually met. And it was surprisingly difficult to avoid this, because all our simulations were fit to configurations were quite close to equilibrium. And when we do this very dramatic melting, then we get very dramatic simulations that go explore all sorts of configuration space, some of them which actually was tending to actually break this condition. So we had to put in some sort of fix the simulation when it was coming close to this configuration. Had to avoid these particular, I put in extra forces to avoid these particular configurations. Nevertheless, it all eventually worked, and we moved on to silicon, which is one of our main interests, and fitted some new electronic temperature dependent potentials fitted for silicon, which are actually based on our Tersov model, but of course there's many, many parameters, and there's many ways of actually fitting these to a small number of finite temperature DFT simulations. But we focused on two things, and that was actually these two parameters here on the Tersov potential, if you're familiar with that. We fit those for the electronic temperature, and also softening. So basically we weakened the bond directionality, which we know should happen. So we then had a set of potentials, and we could run these large-scale simulations for silicon. And they actually agreed pretty well with experiments, such as experiments were, which had been done some time ago, and also other DFT simulations, ab initio simulations. Our line was a solid one, The open circles were previous DFT, two temperature ab initio simulations, electrodynamics, and you could see this very rapid melting. The experiments are the solid dots, which actually show slightly slower melting. So what we basically have is we've got a nice crystal of silicon, fire laser pulse at it, and within 500 femtosecond, because of these what we call non-thermal melting effects, because of the weakening of the bonds, or the weakening of the directionality of the bonds, more like, we get this amorphous silicon formed. So just to summarize, I've gone on a little bit too long, our two-temperature modeling works very well for low to moderate electronic excitations, but for high electronic excitations, we have to modify the interatomic interactions, and this will give us very rapid or non-thermal melting. And also in the case of tungsten, we get these solid phase transformations. But we can include these potentials into our two-temperature MD, and then we can do very large-scale simulations. But we have to be aware of energy conservation. So I'm going to finish there, but I would like to acknowledge the many people that actually contributed to this work over the years. From my group, Robert, Simon, Sam and Galvin, and from Alex's group at the time, Evelyn and Matt, and also our experimental collaborator, Katsumi, and the people that helped us put it into DL Poly, and of course, all our funders. I will finish there and answer any questions that you have.
Thank you very much, Dorothy. So Martin has quite a lengthy question. So Martin, if you'd like to switch your video back on and your microphone, you could ask Dorothy directly.
It's not really a lengthy question. It's more just a comment, although it's a lengthy comment. But the phonon spectra you showed, I think, are not, the instabilities would not give you a transition between FCC and BCC, because the instabilities are at the zone boundaries. So they will presumably be showing you some other potential instabilities. The FCC to BCC or vice versa are essentially preserve the size of the primitive unit cell. So in the phonon spectra, if such a transition were to show up in phonons, that would be in the acoustic modes at the gamma point. So I think what you're seeing in the phonon spectra is some other possible instabilities. I mean, not that they may actually exist, because your FCC, BCC are quite likely, I think, to still dominate. But I don't think the phonons are actually pointing to the transition to FCC. I think they are showing you something different.
Okay, well, I hadn't been aware of that, but I'm quite sure that you're right. I think the free energy diagram is probably showing at least there is an instability. Would you agree with that?
I certainly would agree that there's a good chance that it's FCC that is relevant, because that's showing up in the other parts of your simulation. So I'm sure that bit is right. I'm just...
Having said that, we could also do the same for HCP, and we got the same thing. Yes. So it could be HCP, and it could be FCC, or it could be a mixture of both. Yes. But yeah, I wasn't aware of that particular aspect of the phonon spectrum.
Your instabilities are at the end point. Not sure I can remember what the end point is in this material, but that may be something slightly different.
Okay, thank you for that.
Thank you. So Johannes, you have a question.
Yeah, I thought this is, I mean, I enjoyed this connection with the two-temperature model and the atomistic MD, but I feel like you have to be careful, right, to make this connection, because when you say you discretize your space into voxels, and then within each voxel, I guess you assume that temperature is constant. So I was just wondering, you know, because
the electronic temperature is constant.
Right, but I mean, to define temperature, I guess you have to look at something that has already a certain size. So how sensitive are these simulations to the discretization that you use in space?
They're not particularly sensitive, because actually the thermal conductivity of the electrons is pretty fast. Okay, so in terms, it flattens out quite quickly. So there's not much variation across the atomistic cell of the electronic temperature. clearly in terms of defining the lattice temperature, so we just, because of the energy conservation, it relates back to the average kinetic energy in the cell. And that doesn't necessarily, if we're talking about cascade simulations, when you've got one particular very fast atom, then you have to remove such things from the cell. So you have to be a little bit careful how you discretize those, but it actually doesn't make a huge amount of difference. We usually have, you know, several hundred atoms in our simulation cell, and the energy conservation comes in because it's an average kinetic energy of this particular voxel. So it doesn't necessarily have to be a thermalized distribution within these voxels.
Okay.
I'm not sure if that answered your question. We're concerned about the lattice temperature or the electronic temperature?
I was thinking about the first or second slide where you showed basically that you're doing the two-temperature model, you're solving it, then you're discretizing it, and then you're using the temperature that comes out, I guess you mean the lattice temperature, and put that into the thermostat of your MD.
No, the thermostat is actually coming from the electronic temperature. So you're effectively thermostating your lattice from the electronic temperature, which is evolving in time. And then in order to exchange energy here, then you're relating the lattice temperature to the average kinetic energy in one of these voxels. So that can be a little bit dubious if you haven't really thermalized the energy in one of these voxels, if you haven't got many atoms. And we actually have hundreds of atoms, so it's not macroscopic, but it's not as small as I've shown it in the picture here.
But is the temperature discontinuous? You know, I mean, so your MD simulation cell contains a number of these little discretization cells. Mm-hmm. And I guess, is the temperature discontinuous? The
electronic temperature is continuous. The lattice temperature, it just depends on the cell. But of course, you know, it may be different in each of these, but it doesn't actually matter because, you know, there's nothing happening in here other than this energy exchange where you have got this stochastic force coming from the electronic temperature.
Okay.
So it doesn't matter if the lattice temperature is different in neighboring cells. This is just a way of exchanging energy between the two systems, which is a way of actually putting energy in or taking energy out of your lattice locally. But the electronic temperature is continuous because it's really just defined. We've had these voxels so we can actually solve it numerically, and so as we can actually relate it to a certain group of atoms.